Hello friends, this is Jim with Science Talk. In this video, I'm going to be discussing the dwarf planet Ceres. Very interesting couple of studies involving Ceres. Water on dwarf planet Ceres is driving an active surface. Growing patches of ice and minerals associated with liquid water reveal that the dwarf planet Ceres is still evolving. Researchers studying the warmer region of Ceres, the largest object in the asteroid belt between Mars and Jupiter, have noticed that a patch of ice has grown larger over time. In addition, a separate team found carbon-rich minerals on Ceres' surface that do not last long. Together, the new discoveries suggest that water still has a powerful presence on the tiny world. Using NASA's Dawn spacecraft, the researchers studied the surface of the dwarf planet. The first team, led by Andrea Rapponi of the Italian National Institute for Astrophysics, INAF, found a growing patch of ice on Julian crater, which is found in mid-latitudes. They suspect that water from the crater floor is condensing on the wall, causing a patch of ice to grow larger. The second team, led by Filippo Giacomo Carrozza, also of INAF, surveyed the carbon-rich minerals on the dwarf planet and mapped several regions in detail, revealing changes in the soil that they suspect are tied to carbonates. The water-rich or hydrated minerals suggest that water has risen to the surface and boiled off, leaving the carbonates behind to reveal its presence. Now, before I continue, how could water boil off if this world is cold? Probably most likely because Ceres does not have a strong atmosphere, there's not a high PSI, and so basically since the vapor pressure is such that at low pressure, water can easily boil off. This is a problem that mountaineers at very high altitudes, being the Himalayas, the Andes, and so forth, when they want to boil water to, say have hot tea or whatever, because the partial pressure is so reduced, the air is so much thinner at elevation, the water is able to reach boiling point and escape into the gaseous state at a much lower temperature. That's most likely what's happening here on Ceres. So, going back to what Professor Rapponi said, the same process could be at work at the crater floor of Julian, providing a replenishment of water under the soil that sublimates and in part condenses on the cold wall. Now, sublimation is the process from which a solid goes directly to gaseous, skipping over the liquid phase. Okay? That can happen, say you have frozen carbon dioxide. That will quickly become gaseous carbon dioxide. If you have a lot of snow in a very cold, dry place, and as you warm up into say about 10 degrees Celsius or something like that, that instead of melting, a lot of time that snow, because there's very little water vapor in the atmosphere, that snow just goes bang right into the gaseous state. Which is nice. It's convenient. You don't have much of a flooding issue when a lot of snow melts. But that's what sublimation is. It's the process of going directly from the solid phase or state to the gaseous state. The two works show that water is currently available on the surface of Ceres and produces geological and mineralogical changes on the surface. Ceres is classified as both a dwarf planet and an asteroid. When the Dawn spacecraft arrived at Ceres in 2015, it basically found a nearly featureless world with a rocky surface. A single mountain, Ahuna Mons, rose from the surface. Bright spots within craters were the only color variations on the otherwise pretty much dullish grayish world. As scientists continued to study Ceres, they found hints that Ahuna Mons was not just a mountain, but a cryovolcano. Cryovolcano is also called an ice volcano. So instead of spewing from the magma chamber, spewing lava, it spews ice. Thick water ice may have risen to the surface in the past, flooding the plains with ice lava. Researchers found hints that other icy cryovolcanoes may have dotted Ceres in the past before slowly easing back into the landscape, their heights spreading outward across the landscape. Kind of doing one of those deals. Eventually, dawn revealed that the 130 bright patches contained sodium carbonates, salts that form on Earth as water evaporates from a body of water like a lake or in hot springs. Basically, if you have carbonaceous rocks, like what you find, say, in the Midwest here in the U.S. or U.S. and basically central Canada, when you dissolve that, you dissolve out the carbonate ion, so you can form sodium carbonates, calcium carbonate, and so on. It's difficult for water to stick around on Ceres' surface. The lack of atmosphere on the small world means that sunlight causes the liquid to boil away immediately, leaving behind the rest of the minerals carried with it to the surface, such as carbonate. Because of the low pressure, the water you don't even have to heat it up to 100 C or 212 Fahrenheit. As soon as the heat receives some energy, it evaporates. Carbonates are minerals that are very important because they can give us information about the presence of water on Ceres in the past and the present. So says Professor Carozzo. Carozzo's team mapped the entire surface of Ceres using the Dawn's visible and infrared spectrometer, looking for carbonates. The results reveal that some of the regions required different forms of the sodium carbonates that Dawn had identified previously. The new traces of sodium carbonates are more likely to carry water inside their structure than those found before, as their signals are a close match to minerals such as trona and thermonatrite. Okay, let's distinguish these are. Trona is a sodium carbonate with 2 water molecules in its structure. When we observe it on a planetary surface, we are sure that water played a role in its formation. So in other words, it's like a hydrate. Well, think of methane hydrate, which is frozen methane and water combined together. Okay? This is basically water incorporated into the sodium carbonate. Now, sodium carbonate, the carbonate ion has a charge of -3 on it. Sodium has a charge of +1, so you would need 3 sodium ions to combine with a single carbonate ion to form an ionic compound. And so forming this compound, it is able to fit in 2 water molecules in its structure. Dawn's results revealed that most of the sites rich in sodium carbonate are found in the younger terrains along domes and mounds, as well as in the material thrown off by the impact that formed craters. While it is possible that the carbonates could form in the heat of the impact, the researchers favor the idea that brines, salt, beneath the surface welled up to ooze through the crust. Such cryovolcanism requires that Ceres' internal temperatures stay warm enough to keep water from freezing completely, remaining instead as cryomagma that's rich in sodium carbonates. So now, how does it stay warm? That's an interesting question. Is it? It's not large enough to. Does it have a magnetic field in the inside? I am not sure. So it is not clear to me, and I think that's a question that needs to be answered, as to how can that water stay warm. So while Carozzo's research focused on mapping the entire surface of Ceres, Raponi's study targeted a specific crater. And by the way, these guys are all part of the same research team, so they were basically authors on the 2 papers that were published. So Raponi studied Julian Crater that has a patch of ice on its northern wall. It used, again, Dawn's visible infrared mapping spectrometer. and they were able to watch the ice grow from 3.6 square kilometers to 5.5 square kilometers over 6 months. There are two ways they postulate this ice can grow. The first possibility is that the ice could already exist beneath the shallow exterior. Previous studies have shown that water ice covers much of the dwarf planet's subsurface, and then landslides along the side of the crater could slowly reveal the material. In that case, the ice itself wouldn't be getting larger, rather it would be uncovered slowly. However, based on their analysis, the team's preferred solution involves water vapor. Geological formations similar to Earth's rock glaciers cross the floor of the crater, with a large one at the base of the northern wall. The rock walls may be the source of the ice, as the crater wall traps water molecules coming from just beneath the crater floor. The second way, which is what they suggest, is that the liquid water percolating, and it's related to what I just described, liquid water is percolating under the surface and then freezing to the surface of the cold wall when exposed. The process would require a source of heat that is currently unknown. You heard me just mention this a few moments ago. The increasing solar input, because of the changing season and decreasing distance of Ceres from the sun, could be the driving force of the sublimation of water from the subsurface of the floor, that then in part condenses on the surface of the shadowed wall. What do you mean by the decreasing distance? Ceres is traveling in an elliptical orbit. You have periods in its orbit where it's closest to the sun and furthest from the sun, perihelion, aphelion. So that's basically what that is alluding to. Professor Raponi points out that Carosa's research suggested a source of water-rich material rising from beneath the surface as the source of hydrated carbonates. A similar process could replenish the rock glacier on the crater floor, providing a source of water that helps to grow the icy region. Basically, the upshot of all of this, Ceres is not simply an inert ball of rock, but it's a constantly evolving icy world. In general, the two works show that water is currently available on the surface of Ceres and produces geological, mineralogical changes on its surface. Both papers were published in the March 14th issue of the journal Science Advances. It's always interesting to see reports and studies from other objects in our solar system. And what this is indicating, along with the thought that Io has perhaps cryovolcanoes, Europa is thought to have an ocean, Enceladus is thought to have an ocean underneath the ice, and so forth, is that if we have evidence of water all around the solar system, can it be too far behind to postulate the existence of at least microbes? The only way we'll know that for sure is to actually go there, take samples, and test them. Well, if you like this video, please share. I hope you'll consider becoming a patron at my patreon.com/Science Talk with Jim Massa page. If you're already a patron, thank you for your continued support. Please share, please subscribe, please tell others of the work I do. Thank you.